Curium is a transuranic radioactive chemical element with symbol Cm and atomic number 96. This element of the actinide series was named after Marie and Pierre Curie. Both were known for their research on radioactivity. Curium was first intentionally produced and identified in July 1944 by the group of Glenn T. Seaborg at the University of California, Berkeley. The discovery was kept secret and only released to the public in November 1945. Most curium is produced by bombarding uranium or plutonium with neutrons in nuclear reactors. 1 ton of spent nuclear fuel contains about 20 grams of curium. Curium is a hard, dense, silvery metal with a relatively high melting point and boiling point for an actinide. Whereas it is paramagnetic at ambient conditions, it becomes antiferromagnetic upon cooling, and other magnetic transitions are also observed for many curium compounds. In compounds, curium usually exhibits valence +3 and sometimes +4, and the +3 valence is predominant in solutions. Curium readily oxidizes, and its oxides are a dominant form of this element. It forms strongly fluorescent complexes with various organic compounds, but there is no evidence of its incorporation into bacteria and archaea. When introduced in the human body, curium accumulates in the bones, lungs and liver, where it promotes cancer. All known isotopes of curium are radioactive and have a small critical mass for a sustained nuclear chain reaction. They predominantly emit I+ or- particles, and the heat released in this process can potentially produce electricity in radioisotope thermoelectric generators. This application is hindered by the scarcity, high cost and radioactivity of curium isotopes. Curium is used in production of heavier actinides and of the 238Pu radionuclide for power sources in artificial pacemakers. It served as the I+ or- source in the alpha particle X-ray spectrometers installed on several space probes, including the Sojourner, Spirit, Opportunity and Curiosity Mars rovers and the Follow lander on Comet 67P Churyumov-Gerasimenko, to analyze the composition and structure of the surface. History. Although curium had likely been produced in previous nuclear experiments, it was first intentionally synthesized, isolated and identified in 1944, at the University of California, Berkeley, by Glenn T. Seaborg, Ralph A. James, and Albert Giosso. In their experiments, they used a 60-inch cyclotron. Curium was chemically identified at the Metallurgical Laboratory at the University of Chicago. It was the third transuranium element to be discovered, even though it is the fourth in the series. The lighter element americium was unknown at the time. The sample was prepared as follows. First, plutonium nitrate solution was coated on a platinum foil of about 0.5 cm to area. The solution was evaporated and the residue was converted into plutonium oxide by annealing. Following cyclotron irradiation of the oxide, the coating was dissolved with nitric acid and then precipitated as the hydroxide using concentrated aqueous ammonia solution. The residue was dissolved in perchloric acid, and further separation was carried out by ion exchange to yield a certain isotope of curium. The separation of curium and americium was so painstaking that the Berkeley group initially called those elements pandemonium and delirium. The curium-242 isotope was produced in August 1944 by bombarding 239Pu with I+ or- particles to produce curium with the release of a neutron. Curium-242 was unambiguously identified by the characteristic energy of the I+ or- particles emitted during the decay. The half-life of this alpha decay was first measured as 150 days and then corrected to 162.8 days. Another isotope 240 cm was produced in a similar reaction in March 1945. The half-life of the 240 cm I+ or- decay was correctly determined as 26.7 days. The discovery of curium, as well as americium, in 1944 was closely related to the Manhattan Project. The results were confidential and declassified only in 1945. Seaborg leaked the synthesis of the elements 95 and 96 on the U.S. radio show for children, The Quiz Kids, 5 days before the official presentation at an American Chemical Society meeting on November 11, 1945, when one of the listeners asked whether any new transuranium element beside plutonium and neptunium had been discovered during the war. The discovery of curium, their production and compounds were later patented, listing only Seaborg as the inventor. The new element was named after Marie Curie and her husband Pierre Curie, who are noted for discovering radium and for their work in radioactivity. It followed the example of gadolinium, a lanthanide element above curium in the periodic table, which was named after the explorer of the rare earth elements Johann Gadolin. As the name for the element of atomic number 96, we should like to propose curium, with symbol Cm. The evidence indicates that element 96 contains 7 5f electrons and is thus analogous to the element gadolinium with its 7 4f electrons in the regular rare earth series. On this base, element 96 is named after the Curies in a manner analogous to the naming of gadolinium, in which the chemist Gadolin was honored. The first curium samples were barely visible, and were identified by their radioactivity. Louis Werner and Isidor Perlman created the first substantial sample of 30 microgram curium-242 hydroxide at the University of California in 1947 by bombarding americium-241 with neutrons. Macroscopic amounts of curium fluoride were obtained in 1950 by W. W. T. Crane, J. C. Wallman and B. B. Cunningham. Its magnetic susceptibility was very close to that of GDF3, providing the first experimental evidence for the +3 valence of curium in its compounds. Curium metal was produced only in 1951 by reduction of curium fluoride with barium. Characteristics Physical equals. A synthetic, radioactive element, curium is a hard dense metal with silvery white appearance and physical and chemical properties resembling those of gadolinium. Its melting point of 1340 degrees Celsius is significantly higher than that of the previous transuranic elements neptunium, plutonium and americium. In comparison, gadolinium melts at 1312 degrees Celsius. The boiling point of curium is 3110 degrees Celsius. With a density of 13.52 grams per centimeter 3, curium is significantly lighter than neptunium and plutonium, but is heavier than most other metals. Between two crystalline forms of curium, the I plus or minus Cm is more stable at ambient conditions. It has a hexagonal symmetry, space group P63/mmc, lattice parameters A equals 365 pm and C equals 1182 pm, and 4 formula units per unit cell. The crystal consists of a double hexagonal close packing with the layer sequence ABAC, and so is isotopic with I plus or minus lanthanum. At pressures above 23 GPa, at room temperature, I plus or minus Cm transforms into I squared Cm, which has a face-centered cubic symmetry, space group FM3m, and the lattice constant A equals 493 pm. Upon further compression to 43 GPa, curium transforms to an orthorhombic I-cube Cm structure similar to that of I plus or minus uranium, with no further transitions observed up to 52 GPa. These three curium phases are also referred to as CMI, 2 and 3. Curium has peculiar magnetic properties. Whereas its neighbor element americium shows no deviation from Curie-Weiss paramagnetism in the entire temperature range, I plus or minus Cm transforms to an antiferromagnetic state upon cooling to 65 K, and I squared Cm exhibits a ferromagnetic transition at about 205 K. Meanwhile, curium pnictides show ferromagnetic transitions upon cooling, 244 Cmn and 244 Cms at 109 K, 248 Cmp at 73 K and 248 Cmsb at 162 K. Similarly, the lanthanide analog of curium, gadolinium, as well as its pnictides also show magnetic transitions upon cooling, but the transition character is somewhat different. GD and GDN become ferromagnetic, and GDP, GDS and GDSB show antiferromagnetic ordering. In accordance with magnetic data, electrical resistivity of curium increases with temperature about twice between 4 and 60 Ka, and then remains nearly constant up to room temperature. there is a significant increase in resistivity over time due to self-damage of the crystal lattice by alpha radiation. This makes uncertain the absolute resistivity value for curium. The resistivity of curium is similar to that of gadolinium and of the actinides plutonium and neptunium, but is significantly higher than that of americium, uranium, polonium and thorium. Under ultraviolet illumination, curium, 3, ions exhibit strong and stable yellow-orange fluorescence with a maximum in the range about 590–640 nanometers depending on their environment. The fluorescence originates from the transitions from the first excited state 6d7/2 and the ground state 8s7/2. Analysis of this fluorescence allows monitoring interactions between Cm(3) ions in organic and inorganic complexes. Chemical curium ions in solution almost exclusively assume the oxidation state of +3, which is the most stable oxidation state for curium. The +4 oxidation state is observed mainly in a few solid phases, such as CmO2 and CmF4. Aqueous curium, 4, is only known in the presence of strong oxidizers such as potassium persulfate, and is easily reduced to curium, 3, by radiolysis and even by water. The chemical behavior of curium is different from the actinides thorium and uranium, and is similar to that of americium and many lanthanides. In aqueous solution, the Cm3+ ion is colorless to pale green, and Cm4+ ion is pale yellow. The optical absorption of Cm3+ ions contains 3 sharp peaks at 375.4, 381.2 and 396.5 nanometers, and their strength can be directly converted into the concentration of the ions. The +6 oxidation state has only been reported once in solution in 1978, as the Curie ion, CmO2+, 2. This was prepared from the beta decay of americium-242 and the americium, B, ion 242MO+, 2. Failure to obtain Cm, 6, from oxidation of Cm, 3, and Cm, 4, may be due to the high Cm4+/Cm3+ ionization potential and the instability of Cm, B. Curium ions are hard Lewis acids and thus form most stable complexes with hard bases. The bonding is mostly ionic, with a small covalent component. Curium in its complexes commonly exhibits a 9-fold coordination environment, within a trigonal prismatic geometry. Isotopes About 20 radioisotopes and 7 nuclear isomers between 233 cm and 252 cm are known for curium, and no stable isotopes. The longest half-lives have been reported for 247 cm and 248 cm. Other long-lived isotopes are 245 cm, 250 cm and 246 cm. Curium-250 is unusual in that it predominantly decays via spontaneous fission. The most commonly used curium isotopes are 242 cm and 244 cm with the half-lives of 162.8 days and 18.1 years, respectively. All isotopes between 242 cm and 248 cm, as well as 250 cm, undergo a self-sustaining nuclear chain reaction and thus in principle can act as a nuclear fuel in a reactor. As in most transuranic elements, the nuclear fission cross-section is especially high for the odd-mass curium isotopes 243 cm, 245 cm and 247 cm. These can be used in thermal neutron reactors, whereas a mixture of curium isotopes is only suitable for fast breeder reactors since the even-mass isotopes are not fissile in a thermal reactor and accumulate as burn-up increases. The mixed oxide fuel, which is to be used in power reactors, should contain little or no curium because the neutron activation of 248 cm will create californium. This is strong neutron emitter, and would pollute the back end of the fuel cycle and increase the dose to reactor personnel. Hence, if the minor actinides are to be used as fuel in a thermal neutron reactor, the curium should be excluded from the fuel or placed in special fuel rods where it is the only actinide present. The table to the right lists the critical masses for curium isotopes for a sphere, without a moderator and reflector. With a metal reflector, the critical masses of the odd isotopes are about 3–4 kilograms. When using water as the reflector, the critical mass can be as small as 59 gram for 245 centimeters, 155 gram for 243 centimeters and 1550 gram for 247 centimeters. There is a significant uncertainty in these critical mass values. Whereas it is usually of the order 20%, the values for 242 centimeters and 246 centimeters were listed as large as 371 kilograms and 70.1 kilograms, respectively, by some research groups. Currently, curium is not used as a nuclear fuel owing to its low availability and high price. 245 centimeters and 247 centimeters have a very small critical mass and therefore could be used in portable nuclear weapons, but none have been reported thus far. Curium-243 is not suitable for this purpose because of its short half-life and strong I+ or - emission which would result in excessive heat. Curium-247 would be highly suitable, having a half-life 647 times that of plutonium-239. Occurrence equals. The longest-lived isotope of curium, 247 centimeters, has a half-life of 15.6 million years. Therefore, any primordial curium, that is curium present on the Earth during its formation, should have decayed by now. Curium is produced artificially, in small quantities for research purposes. Furthermore, it occurs in spent nuclear fuel. Curium is present in nature in certain areas used for the atmospheric nuclear weapons tests, which were conducted between 1945 and 1980. So the analysis of the debris at the testing site of the first U.S. hydrogen bomb, IV Mike beside Einsteinium, fermium, plutonium and americium also revealed isotopes of berkelium, californium and curium, in particular 245 centimeters, 246 centimeters and smaller quantities of 247 centimeters, 248 centimeters and 249 centimeters. For reasons of military secrecy, this result was published only in 1956. Atmospheric curium compounds are poorly soluble in common solvents and mostly adhere to soil particles. Soil analysis revealed about 4,000 times higher concentration of curium at the sandy soil particles than in water present in the soil pores. An even higher ratio of about 18,000 was measured in loam soils. The transuranic elements from americium to fermium, including curium, occurred naturally in the natural nuclear fission reactor at Oklo, but no longer do so. Synthesis equals isotope preparation equals. Curium is produced in small quantities in nuclear reactors, and by now only kilograms of it have been accumulated for the 242 centimeters and 244 centimeters and grams or even milligrams for heavier isotopes. This explains the high price of curium, which has been quoted at $160–185 per milligram, with a more recent estimate at $2,000 per gram for 242 centimeters and $170 per gram for 244 centimeters. In nuclear reactors, curium is formed from 238U in a series of nuclear reactions. In the first chain, 238U captures a neutron and converts into 239U, which via I² decay transforms into 239Np and 239Pu. Further neutron capture followed by I² decay produces the 241M isotope of americium which further converts into 242 centimeters. For research purposes, curium is obtained by irradiating not uranium but plutonium, which is available in large amounts from spent nuclear fuel. Much higher neutron flux is used for the irradiation that results in a different reaction chain and formation of 244 centimeters. Curium-244 decays into 240Pu by emission of alpha particle, but it also absorbs neutrons resulting in a small amount of heavier curium isotopes. Among those, 247 centimeters and 248 centimeters are popular in scientific research because of their long half-lives. However, the production rate of 247 cm in thermal neutron reactors is relatively low because of it is prone to undergo fission induced by thermal neutrons. Synthesis of 250 cm via neutron absorption is also rather unlikely because of the short half-life of the intermediate product 249 cm, which converts by I² decay to the berkelium isotope 249 Bk. The above cascade of reactions produces a mixture of different curium isotopes. Their post-synthesis separation is cumbersome, and therefore a selective synthesis is desired. Curium-248 is favored for research purposes because of its long half-life. The most efficient preparation method of this isotope is via I+ decay of the californium isotope 252 Cf, which is available in relatively large quantities due to its long half-life. About 35 to 50 mg of 248 cm is being produced by this method every year. The associated reaction produces 248 cm with isotopic purity of 97%. Another interesting for research isotope 245 cm can be obtained from the I+ decay of 249 Cf, and the latter isotope is produced in minute quantities from the I² decay of the berkelium isotope 249 Bk. Metal preparation equals. Most synthesis routines yield a mixture of different actinide isotopes as oxides, from which a certain isotope of curium needs to be separated. An example procedure could be to dissolve spent reactor fuel in nitric acid, and remove the bulk of the uranium and plutonium using a PUREX type extraction with tributyl phosphate in a hydrocarbon. The lanthanides and the remaining actinides are then separated from the aqueous residue by a diamide-based extraction to give, after stripping, a mixture of trivalent actinides and lanthanides. A curium compound is then selectively extracted using multi-step chromatographic and centrifugation techniques with an appropriate reagent. This triazinyl bipyridine complex has been recently proposed as such reagent which is highly selective to curium. Separation of curium from a very similar americium can also be achieved by treating a slurry of their hydroxides in aqueous sodium bicarbonate with ozone at elevated temperature. Both americium and curium are present in solutions mostly in the +3 valent state. Whereas americium oxidizes to soluble Am(4) complexes, curium remains unchanged and can thus be isolated by repeated centrifugation. Metallic curium is obtained by reduction of its compounds. Initially, curium fluoride was used for this purpose. The reaction was conducted in the environment free from water and oxygen, in the apparatus made of tantalum and tungsten, using elemental barium or lithium as reducing agents. Another possibility is the reduction of curium oxide using a magnesium-zinc alloy in a melt of magnesium chloride and magnesium fluoride. Compounds and reactions. Oxides curium readily reacts with oxygen forming mostly CM2O3 and CMO2 oxides, but the divalent oxide CMO is also known. Black CMO2 can be obtained by burning curium oxalate 3, nitrate 3, or hydroxide in pure oxygen. Upon heating to 600 to 650 degrees Celsius in vacuum, it transforms into the whitish CM2O3. Alternatively, CM2O3 can be obtained by reducing CMO2 with molecular hydrogen. Furthermore, a number of ternary oxides of the type M2, CMO3 are known, where M stands for a divalent metal, such as barium. Thermal oxidation of trace quantities of curium hydride has been reported to produce a volatile form of CMO2 and the volatile trioxide CMO3, one of the two known examples of the very rare +6 state for curium. Another observed species was reported to behave similarly to plutonium tetroxide and was tentatively characterized as CMO4, with curium in the extremely rare +8 state. However, new experiments seem to indicate that CMO4 does not exist. The colorless curium fluoride can be produced by introducing fluoride ions into curium containing solutions. The brown tetravalent curium Fluoride on the other hand is only obtained by reacting curium fluoride with molecular fluorine. A series of ternary fluorides are known of the form A7CM6F31, where A stands for alkali metal. The colorless curium chloride is produced in the reaction of curium hydroxide with anhydrous hydrogen chloride gas. It can further be converted into other halides, such as curium bromide and curium iodide, by reacting it with the ammonia salt of the corresponding halide at elevated temperature of about 400–450 degrees Celsius. An alternative procedure is heating curium oxide to about 600 degrees Celsius with the corresponding acid. Vapor phase hydrolysis of curium chloride results in curium oxychloride. Chalcogenides and pnictides sulfides, selenides and tellurides of curium have been obtained by treating curium with gaseous sulfur, selenium or tellurium in vacuum at elevated temperature. The pnictides of curium of the type CMX are known for the elements nitrogen, phosphorus, arsenic and antimony. They can be prepared by reacting either curium hydride or metallic curium with these elements at elevated temperatures. Organic curium compounds and biological aspects Organometallic complexes analogous to uranocene are known also for other actinides, such as thorium, protactinium, neptunium, plutonium and americium. Molecular orbital theory predicts a stable Curisen complex 2Cm, but has not been reported experimentally yet. Formation of the complexes of the type Cm, Nc3 hours 7 BTP, where BTP stands for 2, 6D, 1, 2, 4 trizene 3-il, pyridine, in solutions containing Nc3 hours 7 BTP and Cm3+ ions has been confirmed by EXAFS. Some of these BTP-type complexes selectively interact with curium and therefore are useful in its selective separation from lanthanides and other actinides. Dissolved Cm3+ ions bind with many organic compounds, such as hydroxamic acid, urea, fluorescine and adenosine triphosphate. Many of these compounds are related to biological activity of various microorganisms. The resulting complexes exhibit strong yellow-orange emission under UV light excitation, which is convenient not only for their detection, but also for studying the interactions between the Cm3+ ion and the ligands via changes in the half-life and spectrum of the fluorescence. Curium has no biological significance. There are a few reports on biosorption of Cm3+ by bacteria and archaea, however no evidence for incorporation of curium into them. Applications radionuclides Curium is one of the most radioactive isolable elements. Its two most common isotopes 242 cm and 244 cm are strong alpha emitters. They have relatively short half-lives of 162.8 days and 18.1 years, and produce as much as 120 watts per gram and 3 watts per gram of thermal energy, respectively. Therefore, curium can be used in its common oxide form in radioisotope thermoelectric generators like those in spacecraft. This application has been studied for the 244 cm isotope, while 242 cm was abandoned due to its prohibitive price of around $2,000 per gram. Curium-243 with a 30-year half-life and good energy yield of 1.6 watts per gram could make for a suitable fuel, but it produces significant amounts of harmful gamma and beta radiation from radioactive decay products. Though as an I+ or- emitter, 244 cm requires a much thinner radiation protection shielding, it has a high spontaneous fission rate, and thus the neutron and gamma radiation rate are relatively strong. As compared to a competing thermoelectric generator isotope such as 238 Pu, 244 cm emits a 500 times greater fluence of neutrons, and its higher gamma emission requires a shield that is 20 times thicker about 2 inches of lead for a 1 kW source, as compared to 0.1 in for 238 Pu. Therefore, this application of curium is currently considered impractical. A more promising application of 242 cm is to produce 238 Pu, a more suitable radioisotope for thermoelectric generators such as in cardiac pacemakers. The alternative routes to 238Pu use the reaction of 237Np, or the deuteron bombardment of uranium, which both always produce 236Pu as an undesired byproduct since the latter decays to 232U with strong gamma emission. Curium is also a common starting material for the production of higher transuranic elements and transactinides. Thus, bombardment of 248 cm with oxygen or magnesium yielded certain isotopes of seaborgium and hassium. Californium was discovered when a microgram-sized target of curium-242 was irradiated with 35 MeV alpha particles using the 60-inch cyclotron at Berkeley, 242, 96 cm plus 4, 2 here 245, 98 Cf plus 1, 0 N. Only about 5,000 atoms of californium were produced in this experiment. X-ray spectrometer the most practical application of 244 cm though rather limited in total volume is as I plus or minus particle source in the alpha particle X-ray spectrometers. These instruments were installed on the Sojourner, Mars, Mars 96, Mars exploration rovers and Philocomet lander, as well as the Mars Science Laboratory to analyze the composition and structure of the rocks on the surface of planet Mars. APXS was also used in the Surveyor 5 7 moon probes but with a 242 cm source. An elaborated APXS setup is equipped with a sensor head containing 6 curium sources having the total radioactive decay rate of several tens of millicuries. The sources are collimated on the sample, and the energy spectra of the alpha particles and protons scattered from the sample are analyzed. These spectra contain quantitative information on all major elements in the samples except for hydrogen, helium and lithium. Safety: owing to its high radioactivity, curium and its compounds must be handled in appropriate laboratories under special arrangements. Whereas curium itself mostly emits I plus or minus particles which are absorbed by thin layers of common materials, some of its decay products emit significant fractions of beta and gamma radiation, which require a more elaborate protection. If consumed, curium is excreted within a few days and only 0.05% is absorbed in the blood. From there, about 45% goes to the liver, 45% to the bones, and the remaining 10% is excreted. In the bone, curium accumulates on the inside of the interfaces to the bone marrow and does not significantly redistribute with time. Its radiation destroys bone marrow and thus stops red blood cell creation. The biological half-life of curium is about 20 years in the liver and 50 years in the bones. Curium is absorbed in the body much more strongly via inhalation, and the allowed total dose of 244 cm in soluble form is 0.3 I1/4 C. Intravenous injection of 242 cm and 244 cm containing solutions to rats increased the incidence of bone tumor, and inhalation promoted pulmonary and liver cancer. Curium isotopes are inevitably present in spent nuclear fuel with a concentration of about 20 grams per tonne. Among them, the 245 Cma 248 cm isotopes have decay times of thousands of years and need to be removed to neutralize the fuel for disposal. The associated procedure involves several steps, where curium is first separated and then converted by neutron bombardment in special reactors to short-lived nuclides. This procedure, nuclear transmutation, while well documented for other elements, is still being developed for curium. References: Bibliography, Greenwood, Norman N. Earnshaw, Alan. Chemistry of the Elements. Butterworth Heinemann. ISBN 0080379419. Hallman, Arnold F. and Weiberg, Nils Lubuch der Anorganischen Chemie, 102 edition, De Goethe, Berlin 2007, ISBN 978-3-11-0177770-1. Penniman, R. A. and Keenan T. K. The Radiochemistry of Americium and Curium, University of California, Los Alamos, California, 1960. External links: Curium at the periodic table of videos. NLM Hazardous Substances Data Bank Curium, radioactive.